Welcome to part 3 of this series of presentations about the best methods to convert aldehydes into secondary alcohols. In this video I'll show you some strategies for the use of organosilicon compounds as carbon nucleophiles. Compounds containing carbon-silicon bonds are prepared on a large scale, currently around 7 million tons per year. These are mainly silicones, that is, polymers formed by the controlled hydrolysis of dimethyl dichlorosilane. Silicones are stable toward water and oxygen, are good thermal and electrical insulators, and are used as lubricants, sealants, elastomers, adhesives, and coatings. The monomers required for silicone production are prepared by the Müller-Rochow process, in which elemental silicon is heated with methyl chloride in the presence of a copper catalyst. Besides the desired dimethyl dichlorosilane, some other methyl chlorosilanes are formed during this reaction as well. With chlorobenzene as a starting material, the corresponding phenyl chlorosilanes can be produced. Because of the large scale at which these processes are run, methyl chlorosilanes are relatively inexpensive. As their applications suggest, alkyl silanes are not very reactive, and usually only alkyl groups with some additional activation can be transferred to electrophiles such as aldehydes. In addition to allyl groups, which will be discussed a bit later, sufficiently reactive alkyl groups include alpha-haloalkyl groups, benzyl groups, or alkyl groups containing electron-withdrawing groups in the alpha position. In addition to this structural activation, nucleophilic alkylations with organosilicon compounds usually require either Lewis-base catalysis, for instance with fluoride, or Lewis acid catalysis to enhance the electrophilicity of the aldehyde. Interestingly, alkyl silanes can sometimes be used as synthetic precursors to unstable carbanions, which cannot be generated by deprotonation or halogen-metal exchange. I'll show you some examples later. In this example, benzyl trimethylsilane was used as synthetic equivalent of a benzyl anion. Treatment with a fluoride source in the presence of aliphatic aldehydes led to nucleophilic benzylation of the aldehyde. This example is similar to the previous one. Again, a benzyl silane was used as benzylic carbanion equivalent, but in this instance the stereochemical outcome of the reaction was monitored. The transfer of the benzyl group to the aldehyde occurred mostly with retention of configuration, but some racemization occurred too. Other suitable electrophiles were acetophenone and allyl bromide. Silanes are also capable of transferring dichloromethyl anions to aldehydes, despite the high tendency of such carbanions to undergo alpha elimination and yield carbenes. The starting dichloromethylsilane was prepared by treatment of a mixture of chlorotrimethylsilane and dichloromethane with LDA. Because LDA does not react with chlorotrimethylsilane, no stoichiometric generation of the chloromethyl anion was required, and this strategy therefore enables the silylation of even highly reactive carbanions. When chloromethyl trimethylsilane was treated with a fluoride source in the presence of benzaldehyde, however, no reaction occurred. This shows that neither chloromethyl groups nor methyl groups can be cleaved off from silicon by fluoride under the mild conditions of this example. The enolates of cyclopropane carboxylates are notoriously reactive because delocalization of the negative charge into the carboxylate group implies the formation of an exocyclic double bond and increased ring strain. Therefore, the enolates of cyclopropane carboxylates are much more nucleophilic than non-cyclic ester enolates and quickly undergo Claisen condensation. The corresponding silanes can serve, however, as synthetic precursors of these unstable carbanions, as shown on this slide. Thus, treatment of an alpha-trimethylsilyl cyclopropane carboxylate with fluoride in the presence of an aldehyde gave a low yield of secondary alcohol. Another type of unstable carbanion which can be generated from a silane and used synthetically is the acyl anion. Acyl anions, generated for instance by deprotonation of DMF or by addition of carbon monoxide to polar organometallics, may tautomerize to carbenes and usually dimerize or react with their precursors before reacting with any external electrophile. In general, if there is a strong driving force for a reactive intermediate to tautomerize to a carbene, as in this case the formation of an oxygen-lithium bond, then this intermediate tends to be highly reactive and unstable. Therefore, the trapping of acyl anions by electrophiles only works occasionally, and only at extremely low temperatures, usually below -100°C. If phenyllithium is treated with carbon monoxide, for instance, the main product is diphenylacetophenone, formed by sequential additions of carbon monoxide and phenyllithium to the intermediate acyl anions. If isonitriles are used instead of carbon monoxide, additions of the isonitrile to the intermediate lithiated imines is sometimes observed, but carbon monoxide does not oligomerize in this way. What this reaction illustrates is the high reactivity of the intermediate acyl anions, which, despite their high electron density, add phenyllithium a second time to generate alpha-lithiated alcoholates. This example shows that acyl silanes can react as true synthetic equivalents of acyl anions and yield, upon reaction with electrophiles, the expected products in acceptable yields, without the need of extremely low temperatures. The main advantages of nucleophilic alkylations of aldehydes with alkyl silanes is that silanes are relatively inexpensive and resistant to hydrolysis and oxidation. Because of the low reactivity, these reagents are highly chemoselective and can be used as synthetic equivalents of otherwise inaccessible carbanions. Unfortunately, few alkyl groups are sufficiently reactive to undergo fluoride-mediated desilylation, and the scope of this reaction is therefore narrow. Furthermore, these reactions must be catalyzed and sometimes require elevated temperatures, what may limit the choice of compatible functional groups. Silanes transfer allyl groups to aldehydes much more effectively than alkyl groups. The main reason for this is the beta effect, which refers to the strong stabilization of carbocations in beta position to a silicon or tin atom. This causes an increase of electron density at the gamma carbon of the allyl group. This effect can also be visualized by resonance structures, in which electrons from the metal carbon sigma bond are pushed into the allyl group, or the positive charge is delocalized into the metal by formation of a metallar cyclopropane. This is an example of enantioselective nucleophilic crotylation of an aliphatic aldehyde with crotyl trichlorosilane. Unfortunately, stoichiometric amounts of a chiral diamine were required. The crotylation reaction proceeded with high chemical yield and high diastereo and enantioselectivity. This example is similar to the previous one, but here only 2% of chiral ligand was sufficient to attain high stereoselectivities. The nucleophilic additions to the aldehydes proceeded at low temperature, and neither strong acids nor bases were required. Both alpha-beta unsaturated and enolizable aldehydes could be used as starting materials. This example further shows how readily allyl groups are added to aldehydes from silanes. In this instance, an enantiomerically pure, preformed silylated amino alcohol was used as nucleophile, and the allylation proceeded with high yield and enantioselectivity at -10°C. Let's now turn to arylations. Aryl silanes can act as nucleophilic arylating reagents in the presence of fluoride or Lewis acids. Because of the beta effect, ipsosubstitution is usually observed, that is, the aldehyde attacks the silicon-bound carbon atom. Such arylations proceed particularly smoothly if the arene is electron-rich and contains further substituents that stabilize a positive charge in ortho and para positions to the silicon atom. Fluoride should enhance the beta effect by increasing electron density at silicon further and by weakening the silicon-carbon bond. This is an example of the arylation with thiazole, an electron-rich heteroarene which proceeded without any catalyst. The final treatment with tetrabutylammonium fluoride was only required to cleave the intermediate trimethylsilyl ether. Unsubstituted phenylsilanes are much less reactive than the thiazolylsilane of the previous slide. And in the example sketched here, an excess of fluoride and 120 degrees Celsius were required to bring about the phenylation. This is an example of enantioselective phenylation with the aid of only few percent of a chiral diphosphine. According to the authors, this reaction probably proceeded by transmetallation of silicon to copper, with the diphosphine phenyl copper intermediate being the phenylating reagent. Under similar conditions, also unsubstituted vinyl groups could be used for the preparation of enantiomerically enriched allyl alcohols from aldehydes. A number of side reactions for this transformation have been reported. Most of them occur under acidic reaction conditions, as for instance the formation of benzylic ethers, as shown here. Secondary benzylic alcohols are often sensitive toward acids, and care must be taken not to destroy them during workup. Here, the initially formed alpha-phenyl propargyl alcohol reacted with the second equivalent of alkylsilane, again because of the slightly acidic reaction conditions. Upon fluoride catalysis alone, such twofold alkylations should not occur. Further potential side reactions include conjugate addition of the nucleophile to electron-deficient double and triple bonds. Then, in the presence of protic solvents and fluoride or acids, silanes may undergo protonolysis. A number of other electrophilic groups can also react with silanes, for instance imines, carboxylic esters, ketones, epoxides and reactive halides, what may cause the formation of byproducts. Finally, some catalysts can bring about the oxidation of the starting aldehyde or the secondary alcohol, in particular if these are electron-rich. Many additional examples of the use of silanes as carbon nucleophiles have been reported, and this here is only a small selection to illustrate the synthetic possibilities. Because of the cost of silanes and the relatively large amounts of waste, this reaction can only be used for the production of fine chemicals. The next presentation will be about the use of organotin compounds as carbon nucleophiles for the conversion of aldehydes into secondary alcohols. See you there.